My name is Shravan Virupneni. I'm a faculty member in the math department. I work in scientific computing, and recently we've been looking into quantum and quantum-inspired scientific computing. It's my great pleasure to introduce Dr. Patricia Lee. She did her undergrad at Caltech in 2000, and since then she came here to the University of Michigan Physics Department. She got her PhD from the Physics Department in 2006, and she worked on quantum computing and quantum information even before it was cool. Like her PhD thesis, in fact, was on trapped ion quantum computers and building them. And since then, she has had a distinguished career, first at the US Army National Research Lab, and then at Lockheed Martin, and since 2016, she has been at Honeywell. And recently, there's a new group called Quantinuum, which was a merger of Cambridge Quantum and Honeywell Quantum, where she's been a chief scientist. A couple of years ago, Honeywell built like a really fancy quantum computer. I hope she'll talk about that today. So pleased to have her. Patricia.
Thanks. Thank you.
Hi, thank you. Yeah, I guess this quantum computing is going to be a little bit different than some of the things we heard about earlier today. So I just want to point out that really the history of quantum computing, at least with trapped ion systems I work with, really came through University of Michigan. And so this is one of my the earlier quantum computers, my very first quantum computer that I helped build right here in University of Michigan. This is probably dating back to about 2001. And you can see here, back then we took some pieces of metal, punch holes in it, and trapped ions, and there's our quantum computer. So here's an image of two cadmium ions. Those are our qubits. And wrote a whole thesis about how to control these qubits and make a quantum computer out of it, and also all these techniques that were performed then that were developed here at University of Michigan. We're still using a Quantinuum, and pretty much all the trapped ion quantum computing companies are using these techniques today. So here's a press release from dating back to 2002, talking about sympathetic focus center here in Michigan. Developed this sympathetic cooling between different individual ions. This is how our quantum computers can be so much better in terms of performance compared to others. So I have to say, yeah, this has been a big journey here, and glad to be back. So why should you care about quantum computers? Well, here's a quote from Feynman. Nature isn't classical, damn it, and if you want to make a simulation of nature, you better make it quantum mechanical. And by golly, it's a wonderful problem because it doesn't look so easy. Of course, he didn't have access to a quantum computer. He can only dream about it. Now we actually have quantum computers, and if you want to access it, you just go online. You can access it. And it's been it's a lot of fun. And so obviously simulating nature, simulating a lot of chemicals and maybe condensed matter systems, these Hamiltonians are a big part of it. That's the quantum chemistry, materials, etc. But there are also other applications, such as optimization, which has been a big part of it. So this is just an example of some of the applications that Quantinuum has been working on. Cybersecurity is a sort of an application of a quantum computer as well. I won't talk a whole lot about it today because it's more of using quantum mechanical randomness to generate entropy for secure key generation. So less so about high performance computing, but there are obviously lots of other applications as well besides this quantum chemistry and quantum optimization, but those are the big ones right now. This slide is actually a little bit about our company, Quantinuum. We're what's called a full stack quantum computing company, which means we work both from all the way from the applications and software, as well all the way down to the hardware layer. And so, and then that includes a couple of what we call middleware, these compilation layers that takes these applications and programs that software that helps people write quantum code and actually compile it down to different hardware, and also optimizes and reduces their circuit size while doing so. And so, yeah, we build our own hardware, and so we have everything from the solution all the way down to the qubits. But our software stack also works with other people's quantum computer, and our hardware also accepts software from other people, third-party software as well. A little bit about Quantinuum. We used to be Honeywell Quantum Solutions and Cambridge Quantum. Some of you may have heard of us before. We combined about a year or more ago. And so most of the hardware is based in the US, in Colorado and Minnesota. The software side started out in the UK. And we've expanded to Germany and Japan locations as well. So I'll start by, I wasn't sure what the audience here is, but I want to talk a little bit about where quantum computing gets its power. So with classical computers, you have bits, just zeros and ones. In quantum mechanics, you can have superpositions, right? So we have quantum bits or qubits. They can be simultaneous in some superposition of 0 and 1 at the same time. And so if you imagine if you have n bits, then you can record a number that is, one of those to the n possibilities. In a quantum computer, if you have n qubits, then you can be in the superposition of all 2 to the n at the same states at the same time. And so so the interesting thing is, so you can if you have that kind of resources, then you can compute all those with all those states at the same time. And so if you think about it, 50 qubits is about 1 to the 50 or 1 quadrillion values. Those are complex amplitude that can be stored in those state vectors. And we can compute with all of that at the same time. And this is about on par with what the memory that exists on some of the best supercomputers today. So you can see that really we don't need a lot of qubits to really starting to stress some of the classical resources trying to simulate it. But more than just qubits, you also need to be able to do operations on them. And so for universal quantum computing, you need 2 types of gates. One's a single qubit gate that basically operate on just a single qubit. So classically, for example, you got a NOT gate. On quantum mechanics, you have a square root of NOT gate type of thing, which turns your zeros or 1 into some superposition of 0 and 1. So you need that to put your qubit into some superposition. And then after that, you also need the 2-qubit entangling gate. This is probably the hardest operations for every system out there. And basically, what happens is you need to be able to generate entanglement. So for example, classically, you have this XOR gate that flips a bit, depending on the other bit. In quantum, there's a similar thing called control NOT gate. And except all these, it's the same truth table, but now we have to be able to, the operation has to work for all the different quantum states. So, if we start out with a superposition on qubit 1 and 0 on qubit 2, you run it through a CNOT gate. Now you have this highly entangled state of 0, 0 plus 1, 1. Now, and any operation you apply here, single qubit or two-qubit gate, will apply to all the superposition states. So if you have a two-qubit gate that's performing on 2 out of the 50 qubits, there may be all 2 to the 50 possible amplitudes will change depending on just by that operation. Right? So this thing just scales in balloons. So you say, that's great. You can do all this parallel computing. You have all these resources, huge Hilbert space. So that sounds great. You can just go and compute all these things in parallel, right? Well, there's a catch in quantum mechanics. When you measure these qubits, the waveform collapses, and you only get one number out. So you kind of lost all your benefits there. So the trick here is that these quantum algorithms must be designed to take advantage of this quantum mechanical effects and not just doing parallel processing with classical algorithms. And so just to highlight why quantum algorithms are not the same as classical algorithms, first you have the quantum algorithms, you can use interference effects to amplify the solution of interest. Right? You can compute on all these states, and then at the end, maybe you're only interested in some one result, right? Like give me a number, give me the energy of your ground state or something, right? So what you can do is use interference to just amplify the probability of getting that number. And so you run it and you measure it, and you're very likely going to get that number, right? And if it's, you have some statistics, that's okay. You just run it many times, but it's polynomial rather than some of these computations in quantum that's often exponential, right? Compared to classical algorithms, you have to see, you have to do these computations, one at a time, and you search through your parameter space, and hopefully eventually find the solution. But here in quantum, you can just do it all at once, and then design your algorithm to get the answer you want to pop out. And then one thing to note is that quantum algorithms, the output is probabilistics, right? It's just the nature of quantum mechanics. So very often you have to run it many times, and that's just accepted, right? And those statistics, there are errors sometimes that has to do with statistics, but just the quantum nature of it will demand that you do that. Classically, obviously, output is deterministic, and that's nice. But you don't get that sort of parallelization of all the state vectors at the same time. And this is one big note is, quantum algorithm is not just running classical algorithm on a quantum computer, and you shouldn't expect to give better or faster results. It really is, you have to use a different algorithm, right? You have to design the algorithm, you have to run it differently. It's a totally different thing compared to classical algorithm. And vice versa, if you try to take your classical computer and your supercomputer and try to simulate your quantum algorithm, right? The thing is that thing does not scale well, right? And so I'll show you later that we're at the point where we have quantum advantage where we can design quantum algorithms that are really hard to run on the classical machine. Although there are some quantum-inspired algorithms where people try to design quantum algorithm, and then they realize, hey, they can do this classically without a whole lot of overhead. So those things become classical algorithms. That's a nice speed up. Just as a few examples of quantum algorithms that are known to have theoretically proven to have speed up. Got quantum simulation, obviously. Some Grover search algorithm, that's an Oracle search, that has a quadratic speed up. Factoring for Shor's algorithm, that may be the most famous one. But there's a whole quantum algorithm zoo you can look up online that describes all the nice quantum algorithms that people have published before. But certainly, we say quantum computing is fairly new, so it's hard to beat 50 years of head start, maybe more on the classical side with both the hardware development and also all the computing theory and all the things that that the speakers have talked about today. Certainly a lot of good tricks to optimize, so it's a pretty high bar to compete against. Just mention a few recent Nobel Prizes that's related to quantum information, especially trapped ions here. David Wineland and Nis Boulder really pioneered a lot of the work that we use in trapped ions. And he was awarded a Nobel Prize in 2012, and also this year the Nobel Prize was awarded to Elaine Espé, John Clauser, and Anton Zeilinger, who are really who have done really amazing work on this Bell state inequality and quantum information science. That's really the basis of our quantum computing work. So there are lots of, I'm going to talk, my background is hardware, so I'm going to spend a little bit of time talking about hardware. There are different types of qubits, obviously, out there. There are superconducting, these Josephson junction qubits that probably many of you heard about from IBM, Google, Rigetti, and D-Wave. Today I'm going to talk mainly about trapped ions. That's our technology. And then, but there are others such as neutral atoms, Majorana fermions. These are topological states that are can protect against many of the errors, and also semiconductor quantum dots and photons as well. So, and all those technologies have made huge improvements in recent years. So right now, Quantinuum actually has 2 quantum computers on the cloud. One's running at 20 qubits. One is on an upgrade cycle from 12 qubits to 20 qubits. Well, we have, and here are the fidelity, the errors for the single qubit gates, 2 qubit gates, and etc. here. And you can see these are really so maybe from the classical side, say, well, those errors are actually pretty bad, right? For something like the 2 qubit gate, 3 times 10 to the minus 3 is not a great error compared to classical computing, which you rarely get any error. But these are really the best in industry right now, or best even in many academic settings. So that's where we are, and we actually do keep a pretty tight bound on the performance of our commercial systems on the cloud, so that our users get very consistent performance. What we also measure usually is the state preparation and measurement errors. Often that's that also limits how good your answers are and how many times you have to run your algorithm. And then this is also pretty good in the 10 to the minus 3. And the memory error per, what we call memory error per depth 1 circuit time per qubit, which means these qubits are very delicate things, and they will decohere over time. And so what we quoted instead of a coherence time, which is seconds and such, but we like to quote it in terms of during the time that every qubit gets to do a single qubit gate and 2 qubit gate and get rearranged in our system. That's the errors are in the 10 to the minus 4, and then we also have this crosstalk error. Ours is pretty much negligible because of our hardware. So the point here is I want to point out is just that really 2 qubit gate error is always the worst, the limiting factor, because you have to do this 2 qubit gate over and over and over again. That's really the power of quantum computing. The rest are pretty small in comparison. A state preparation measurement, you really only do it once at the when you measure, so it's not as significant as 2 qubit gate error. And by the way, we have all the data sheet and our benchmarking data online on GitHub if you want to go look it up. Those are the benchmarking metrics for the hardware on sort of individual operation level. We also try to measure how the system overall performs when you run a full-scale circuit on these computers. And so one of the metrics that was actually invented by IBM several years ago was this metric called quantum volume. And so the way you define quantum volume is, if you have n qubits, then you have, and then you randomly pair them, and then you choose a random SU4 operation. So SU4 operation is actually often involves three 2-qubit gates. Okay, and so that's pretty hefty. And then so for n qubits, you have to do n rounds of these randomly paired, 2-qubit gates across all your qubits. And then and then you measure at the end. You randomly choose your SU4 operations, and you randomly choose pairing. And then at the end, you compare with their classical output. And if this heavy output it matches above this 2/3 bar, then you pass the quantum volume test, right? And the quantum volume definition is 2 to the n for n qubits and n depth that you run in your random circuits. And this is a really tough metric and really hard to actually cheat on, because these are random operations. And there are some compiler tricks that you can sort of optimize a little bit, but in general, it's pretty challenging, right? And this 2 to the n really represent the classical resources you need to simulate similar size circuits with a classical computer. And so here's our latest data with n equals 15. This is industry best. I think the next best quantum volume anybody has measured is sort of in the hundreds or maybe 1,000. So you can see that our average is always above the watermark, and then and then we need some statistics and taking a few random circuits to get their error bars to be above that line as well. And so really, so 2 to the 15 is 32,000. It's the first time anybody has ever gotten a quantum volume that high. And you can see we've been measuring that on a system scale since we started making quantum computers, since our first release back in 2020. And we started out with 4 qubits and quantum volume was 16. And we've steadily improved our system. And we've also went from, system model H0 to H1, and these, at launch time, at H1 launch time, the quantum volume was only 128 with 10 qubits. We continuously improve our hardware and software and calibration procedures on our system, and so we were able to make these huge gains in quantum volume. And it's averaging about 10 times a year. That's our goal. That's our stated goal back then, and we've been able to keep up with that trend pretty well. And you can see, this is, for something a random circuit like that, for the 2 to the 15 quantum volume is 244 we call arbitrary angle 2-qubit gate per circuit. Okay, for a quantum computer, that's pretty good. But really, that's only because the quantum volume test requires that passes that 2/3 bar. We've run circuits with maybe a couple thousand 2-qubit gates, and still be able to extract out pretty meaningful answers out of it. This is the hardware that actually performs that we're offering right now over the cloud. It's called quantum CCD, quantum charge coupled device, because these ions are charged particles. They're qubits, and we physically move them around the system, right, like a CCD. And so here's the actual schematic of our trap. Here's a picture of our ion trap, and it has these 5 zones. Marked in blue here, and that's where all the quantum operations happen, and we can do that in parallel. So we can do 5 2-qubit gates in parallel, 5 single qubit case in parallel, 5 initialization, measurement in parallel. Our qubit of choice is a terbium-171 ion using a ground state hyperfine levels. These are effectively atomic clock states, right? So that's how we get our really long coherence times, a really long quantum memory on our qubits. And then we also have these sympathetic cooling ions that was invented here, a method was invented here. We use barium in this case as our buddy for keeping the motional states of our qubits very low, so we can do high fidelity operations. And so here I have some animation here on how the trapped ion works. So here we just loaded an ion by putting sending some neutral atoms through a load hole on the trap itself, and then we use lasers to ionize, and these we apply RF on these rails and DC voltages on these electrodes to really create the trapping potential and capture those ions as they form. And then once we have the ions, we can start moving them around along these RF rails by changing the voltages on our DC electrodes, these little segmented electrodes. And then so there we moved it into a single qubit gate zone, the laser, turn on the laser, and then really is the laser interaction with the ion that does the quantum computation, right? So the trap itself is just moving them around and getting them to the right places to do the interaction. And then here we have to do a 2 qubit gate. Then we have first we have to bring 2 ions together into a single well, and then we send in our laser beam. It's a little more complicated there. And then once it's done, it's 2 qubit gate, we can go ahead and pull them apart and then move them to their next location for their next operation. And so here's some nice fun movies of what's going on there. So here you have 2 ions right there. They start out far apart. When they're combined in the same well, it's actually just the 1 dot. You just see the 1 dot. So here you get 2 locations. They bring them close, go into one dot, and then you separate them back out. And then, of course, the other thing is that this H1 trap is just linear. Everybody's in a row. So sometimes, ions have to go and scoot over each other, like, you're trying to get across to somebody else on the airplane aisle here. And so here's a swap gate where we allow the ions to rotate and change position so they can get across each other to get to meet their partner for the 2 qubit gate. What this architecture gives us is a really nice all-to-all connectivity. So, compared to something like superconducting circuits, where once they make their chip, they can only talk, their qubits can only talk to their nearest neighbors. Here, all the qubits can talk to any other qubit, right? We just physically drag them into the same place. And so, in this sort of fixed nearest neighbor architecture, if you want to talk to a distant qubit, then you kind of have to do a lot of swap gates. And these things are noisy, and you're losing all your quantum information on doing those gates. While here, the transport is very clean, and you don't lose much memory. It's pretty fast. So while you're doing that, we only need 1 gate, and that's the only error you incur. Like I said, our gate fidelity is very high. These are really our industry best. But what this QCCD architecture allows us to do, in addition, is this mid-circuit measurement and qubit reuse. So we can take 1 or 2 or however many qubits in the middle of a quantum circuit. We can measure it, right? And we can record the answer. All the other qubits that haven't been measured get to keep their quantum information. And depending on what we measure on those qubits, we can change the operation going forward, right? It seems like an obvious thing. This is actually really hard to do, and our system is the only commercial quantum computer that can actually do that. And then the nice thing is once you measure those qubits, you can actually reinitialize it and put it back into the system and do your computation. So you actually get a few more qubits than you would expect. And then this conditional logic is absolutely a key and necessary ingredient going forward for fault-tolerant quantum computing. And also, there are other things like measurement-based quantum computing that also uses this conditional logic operation. And so for our roadmap, right now we're here at H1 with a linear trap. Next system is a racetrack. And then we continue on with more and more complicated systems and larger systems. And the idea is that right now we're really in this what's called a noisy intermediate scale quantum era. That's what this is a term coined by John Preskill at Caltech. Basically, we're dealing with physical qubits. They have some fundamental or real world limits to what the errors are, and we have to live with them. And we don't have that many qubits, right? We have tens or hundreds of qubits. But eventually, right, as we scale up, then we want to get in the fault-tolerant quantum computing regime. So as in classical computer, there are ways to do error correction, right? So same with quantum computers. And obviously, those schemes are a little bit more complicated. But the idea is we want to continue to push the error rates on the physical qubit level in the near term. And those in terms will also reduce the overhead we need for fault-tolerant quantum computing. But hopefully by the end of the decade, we would be operating in that fault-tolerant quantum computing regime. And so here's our system model H2. It's the trap's been made. The system is assembled, and you can see lots more ions running around this racetrack. So this trap can support a lot more qubits than our H1 system, and currently it's not even fully packed yet. So a lot of room to grow there, and that system should be coming in the near future. And then for these larger systems, we want to do junction transport, so we can grow the system size in 2 dimensions rather than just 1 dimension. And so this is one of our test chips that we've made with the 2 junctions on the trap. And here is an example of a terbium ion and a barium ion, which is, you can see, is in the halo. And we can move them through the junction in any direction we want. We tried this way back when I was in grad school. And we made our first junction trap, worked very poorly. It was, a lot of times you couldn't even get the ions across the junction, and we could only turn right and not left, and so it's a Michigan left there. We've come a long way since then. That we can really control these ions well through the junction. And so, what is it like to access our quantum computer on the cloud? Well, if you're a user, you just download our API on your laptop, and then you can write your quantum program, and then you connect up to our portal on the cloud, send over the program, and then that program will be run on our hardware. So here's an example of a very simple algorithm. Our interface for the hardware takes OpenQASM. It's a quantum assembly language. And so basically, the programmer doesn't have to care what we're doing with the ions. They just say, I want these gates between these qubits, and that's what's going to happen. And then that gets translated and compiled down to some lower level language, and that gets run on our quantum. And then that is sent to our control system, and run on the hardware, and then we return the results to the user. I remember back in grad school, I used to have to program these things at the pulse level, right? How long do we turn on the laser, and what frequency? All these things are automated now. So, and I just want to say, actually just yesterday, this slide is a day old, and it's already outdated. Yesterday, we announced that we're using a quantum intermediate representation, which is an LLVM representation of the programming language. And actually, we were the first one to actually implement it on the hardware, and already had our beta user are trying doing quantum phase estimation using that. The thing is that these, some things like OpenChasm is pretty early kind of language, so it's very primitive. And a lot of things it just doesn't handle well. So if you want to do loops, if you want to do conditional logic, right? Our conditional logic in OpenChasm, which is our special extension, uses if statement, right? And now you can now write a lot more complicated classical computing routines alongside your quantum routines, and it will run that, right? So you don't have to. You're not stuck with the if statement, which is really not really useful going forward. So a lot of these languages are changing, and a lot of the way we do things are changing as we learn how to do it better, as we try new things. So all computer scientists out there, we'd love to have your input on how we can better design both quantum computing language and how we interface and how we compile and manage that quantum computer. So I'll just come back to here that we do the full stack on our quantum computer and for quantum computing services, and I'll talk a little bit about some of the recent developments. So I wanted to talk a little bit about the quantum advantage, right? People always want to say, well, is quantum computer actually better than classical computer? And so this is a hotly debated topic. So I'll tell you the story about Google. So a couple of years ago, Google, with their Sycamore chip, had 53 qubits. And in 200 seconds, they did this boson sampling kind of problem. And for the cross entropy benchmarking, they claim that in 200 seconds, it would take 10,000 years on a supercomputer to compute the same thing. That was a little bit controversial from day one. People say, it does not take 10,000 years. It's weeks or days or something, but it's still long, right? And so that debate has been ongoing. And so here's, for example, is a recent paper from a Chinese Academy of Science group that they put together 512 GPUs. It took 15 hours to do the same thing as Google, right? So you can debate, okay, fine, is that really a huge advantage or not? But in the meantime, right, obviously the classical computing have improved, so that's quantum computing. And so here's this group from Hefei, China, their newer version of the Google experiment has 66 qubits, and run for 1.2 hours, and they estimate and that takes up 8 years in supercomputer, right? So you can say, well, are these things really useful? Because the quantum computers are just doing what they can do, but it's not really a universal programmable type of quantum of system that we think of. And so are these things really useful? And so I can say that really, there are quantum computers that can run, quantum circuits that can be easily simulated by a classical computer, right? But that doesn't mean that it's useful, right? I mean, this is a toy problem. Does anybody care, right? And so at Quantinuum, we want to make these things practical for our users and solving problems that people care about. And so are there relevant problems that can be solved by a quantum computer, in the near term, as people get to sort of, these even just 50, 60 qubits, it could potentially be computing things that the best supercomputers will be struggling with. And the answer is maybe. There are no definite proven algorithms that really shows a quantum advantage from a quantum computer with sort of up to sort of these near-term noisy intermediate scale systems, but there's a lot of promise, right? So maybe we haven't found the killer application, but people are looking and people are trying. And so here are examples of some of the quantum chemistry simulations that Quantinuum has done with researchers, both industry and academic partners, to look at real world problems, with metals and hydrogen fuel cells, drug designs, etc. And most of these rely on what's called a variational quantum eigensolver algorithm. And so it basically takes a problem, breaks it down to the part that's hard for a classical computer to solve, but easy for quantum computers to solve, and run this problem on a quantum computer, and then look at the answer, plug it into the classical, do some classical calculation to adjust some of the parameters, and then plug it back into the quantum computer to do that. So it's a little bit hybrid quantum computing between your classical computer and quantum computer. And so there are a lot of tools now from Quantinuum in terms of our quantum chemistry software, as well as from Microsoft, who recently just announced they have a sort of these close linked hybrid computing between their classical Azure cluster and the quantum computers, and our quantum computers in specific on their Azure cloud as well. And so, and there are a lot of people talking about plugging in a quantum processor next to a high performance computing cluster, and those are the ideas. I think that may be beneficial going forward doing this hybrid computing. And so here's an example of using our InQuanto software, which is which basically provides the user a lot of the functions for quantum chemistry calculations, so that you don't have to really, so users don't have to code at the quantum assembly language level. And this is an example in collaboration with Ford Motor Company to go and to simulate and look for batteries. And so you can see really, I would say that at 20 qubits, you can still simulate everything from your laptop. It's pretty lightweight. But so what we have to do is break down a very complex problem into smaller and smaller bits and getting it to a size that we can run in today's quantum computer. But the point here is that by going through this process, we built the software tools, we have the example of how to execute it. Now, once we upgrade our quantum computer, our hardware, to a larger number of qubits, then we can actually go and do this all over again with a larger and more complex molecule. And that's the point of the exercise, right? And so you can see these lower two are from our quantum computer running VQE algorithms on our actual hardware, and then the top two data point, the blue data points are from classical simulation, right? It's classical calculation. And so right now you can compare our quantum calculation to the classical calculation, and they match really well, which is good news. But as we scale up our quantum computer, eventually, the classical data may not be available anymore. And then you just have to trust our quantum computer works. And so here's their paper detailing all their work there. Another example this is a condensed matter simulation in collaboration with Andrew Potter at University of British Columbia. This is a simulation of a dynamical topological phase. Basically, for condensed matter people out there, probably familiar with dynamical decoupling. It's basically using a time-dependent interaction with the system to drive these topological protection, right? So that your system actually decays, decays slower, that is more robust to environmental conditions. And so this is a problem that's been in condensed matter, theory for a while, and but there are no physical demonstration of this, and so they implemented it. They coded it up and implemented it on our quantum computer using two kinds of protocol. One's periodic drive, the other is quasi-periodic, and then trying to show that, hey, and it's the first time anybody has implemented this topological phase protection. And as it turns out, it's interesting that we learned was that actually on the periodic drive, it turned out that the data was a little bit worse, actually a lot worse than what was predicted by theory. Assuming our error rates and everything, this thing's decaying much faster, and we ask why. Well, it turns out that our quantum computer has both incoherent errors and coherent errors. Coherent errors are, well, we really drive the, we did a slightly different operation coherently, but it's not quite the same. And so this is actually due to memory error with some of our coherence time. The coherence error, our qubit frequency was drifting a little bit. So those things remain coherent. And then so we picked up on this periodic drive that actually causes faster decay, but not on the quasi-periodic drive. And so we learned that, hey, our system has this coherent error, which we went back and fixed. But then also on the theory side, that we now know that coherent error, this periodic drive does not protect against coherent, or is poor protection, offers poor protection against coherent error. So yeah, there are lots of really cool condensed matter systems that can be implemented on a quantum computer today, and that's one of the areas that's very exciting. I'll just, I'm probably running out short on time, but just a quick word about some quantum optimization. And here's a few examples of industry partnerships that we've just, worked with Deutsche Bahn on some train schedules, optimization, has some oil refinery kind of optimization or job scheduling. Again, these are very simple, very fun, introductory examples right now, very small scale, but they can be extended. And so here's an example of what's called a quantum approximate optimization algorithm, which is what many of the optimization codes are based on. And so because we can do this mid-circuit measurement and reuse the qubits, what we realize is that in a lot of circuits, you're not using all the qubits from the beginning to the end. So once you finish using the qubit, you can just measure it then, and then reinitialize and toss it back into the circuit. So, and so our theory team came up with this qubit reuse compiler that just takes your code and then compile it down using the circuit measurement and see how many fewer qubits you really need. And it turns out that they found this 80 qubits QAOA program actually can be compressed down to 20 qubits and run on our hardware machine. So, and then you get some nice results that's expected from your classical calculation. And so you can see this thing really scales well for certain algorithms. For what we thought or would have taken thousands of qubits now can be compressed down to hundreds of qubits using this technique. These kinds of things happen a lot where people look at a certain algorithm and then they found that, hey, we can actually reduce the cost of actually running it by compressing the number of either compressing the number of qubits or compressing the number of gates that you need to operate on them. And so, these theory work is really helpful as our hardware is trying to scale up and improve. And so here are just some of the examples of our users, what our users have been publishing and have been running on our quantum computer. Here's quantum gravity. We did not make a wormhole in our quantum computer, but some people have lots of fun studying them using our quantum computer. Periodic plane waves, electron structures. There's one for protein folding. This is a stock portfolio optimization from JP Chase. There's one for neutrinos and even modeling fission. So a lot of good work, and it's just in a few months, really people have had great creative ideas on that. Okay, so a quick word about about going forward. we can do, for fault-tolerant quantum computing, what we can do is using multiple qubits to encode a logical qubit, much like the classical error correction, right? You can take 3 qubits, and if one of to encode 3 bits to encode 1 bit, right? You need to get redundancy, and if one of them, failed and had problems, then you can do majority moding, and you can still get your answer. You still won't lose your data. Well, same thing in quantum computing, except these codes are a lot more sophisticated. But you can use multiple physical qubits to encode 1 logical qubit, and then you can operate on them and get much higher fidelity and much less error-prone operations on them, or so the theory goes. And so that's kind of the pipe dream that we want to prove going forward, and many other groups have had some really nice demos recently as well. And so this is one experiment we did about a couple years ago. Basically, this is a scheme where we use 10 qubits, 10 physical qubits to encode a logical qubit. So actually it's 7 data qubits, and then there are 3 physical qubits that are ancillas that go around and probe and check the parity of all your other qubits in your logical qubit. And if the parity check fails, then you know something happened. And something happened to your logical qubit, and then you can go and fix it without measuring your quantum, your logical qubit at all, right? These quantum states, you can't measure it. You can take a look at it. You just have to check and see, hey, did you make a mistake? Did an error occur? We'll fix the error without looking at it. And so all this has to be done coherently. So our experiment was we initialize a qubit. We can do a single qubit gates and rotate it into any state we want. And then we can go through these quantum error correction cycles where we go around and check parity. If there are some checks pan out, that's great. If some checks didn't pan out, we do more checks. And then we record down what errors occurred there. And then we do this over and over again. And then at the end, we sort of take all the accumulated errors in that process. And then at the end, before we measure out the qubit, the logical qubit state, we make the correction, an actual correction, go and fix the logical qubit. And that's the hardest part. I think many people have run through these algorithms, these error correction schemes, but actually doing that real-time correction, right, before your qubits all decohere, you have to do a classical computation to figure out what errors occurred and what gates to apply to fix it. That's the hard part, right? And that's what our system is able to do. And so here's the data for, yes, okay. So I say, yeah, so here's multiple qubit gates, multiple rounds of quantum error correction, but we're not breaking even yet. As in our logical qubit right now, it's not quite as good as our physical qubit, but now we have a system, now our quantum computer can do we can make 2 logical qubits, and we can do a 2-qubit gate on it. And right now, you can see the logical qubit is actually marginally better than our physical qubit fidelity, or 1 minus the error, so it has less error. And then certainly the state preparation and measurement on the logical qubit is a lot better than our physical qubit. So we're like the first time we're seeing this in this fault-tolerant quantum computing scheme, we can drive the error down below what the physical qubits can do. And so finally, I just want to say, quantum computer really is starting to exceed the ability of classical computers to simulate them. And we have significant improvements. We made us and the whole community have made great improvements on the hardware. And that's expected to keep going in the future years. And many problems, are in scientific problems and industrial problems. They can be solved by quantum algorithms, and people are testing them out on real hardware. And so I just want to encourage you to think about how you can take advantage of the quantum computer. Here's the thing, you can get free access to our quantum computer from Oak Ridge. So while you're running your program on Frontier and Titan and all the supercomputers, so please check it out and check out our quantum computing hardware there. Also, Microsoft has a similar program as well for researchers. So thank you very much.
Thank you. So we are running into lunchtime, so we'll take maybe a couple of, one questions. Yeah. Sure, yeah. Any quick question for Patty? Okay, if not, I can ask you one, Patty. So, so you mentioned like at the hardware level, you're doing all these improvements to correct the errors. But at a compiler level, will the vendors be doing like compiler level error correction so that the users don't have to worry about like, running the code and then doing the error correction later?
Yes, yes. So that's part of it is that we are working on trying to build in, right, the compiling it to the error with the error correction in mind, right? And so, yeah, we're just starting on that because, right now it's just 2 qubits, 2 logical qubits. It's not very exciting. But yeah, and the thing is that there are also different error correction codes. So I didn't say that we actually run 2 different types of error correction code. One was the 5-qubit encoding, one was 10-qubit encoding. And so there are different types of code. We don't know which one is best. And we're trying them out and trying to understand what that looks like. Because this is like the first time anybody can actually implement this on hardware. So there's a lot of development work that's there. But we're also working on the compiler, on the compiler side, right? How do we support this? How do we compile it down to, do we let the user choose which code to do, or can user figure out, like, design their own, error correction code and such. And so those things are kind of in that development phase. And yeah, so definitely someday we're going to see that pretty soon.